Okay, it's 5:25, so let's get started. Question.
Can you do an example of what we were talking about last week? Or last class?
I'm going to do some more undecidable problems, yeah. I have two more in plan, if that's what you're referring to.
I mean, just like, I'm having trouble thinking through them logically.
Okay, yeah.
So that's kind of, if you do an example, I'm sure that'll help.
Yeah, I have two planned. Okay, I have a few announcements. P-Set 3 solutions are up, so take a look at those. P-Set 4 is out, has been out. So are there any questions about P-Set 4? Yeah, go ahead.
So I used the substitution in the guide. I consider that to be delete followed by an insert.
Well, delete and then insert, that's two operations.
But I use that to mean one substitution in the when checking. So
Well, that is a substitution by I'd have to see it. Yeah.
The first problem, would you give us bonus credit if we created one for the site, like a regular spreadsheet machine? Like
What do you mean creative one?
the regular,
The regex crossword. Yeah.
No?
I don't know what you mean.
Oh, you can actually upload your own.
Yeah. No.
No? Okay.
But because I assume solutions are available everywhere, so yeah. I mean, you can implement it and it'd be horrendously slow, but show it's decidable at least. Any other questions about P-Set 4? Okay, so I'm going to lecture till around 6:05-ish and then midterm time. All right, so what were we talking about last class? What's that? Not just decidability. We talked about reductions to show what, though? Some prefix of decidability. It's one syllable. Undecidability, yeah. So that's the thing we were talking about before. And so what was the first problem that we showed was undecidable before that? ATM, right? And the way that we showed that it was undecidable was we supposed that we did have a decider for it, and then using that supposed decider, we were able to make a machine that supposedly exists, but we were able to show on some inputs it actually gives us a contradiction. And so therefore that machine can't exist. But the only way it could is if we assumed that ATM was decided by something, yeah.
So the thing that I guess I was confused about is how you can get all those parts and just kind of put them together. Like in the video, I don't know if anyone's watched that, the one that was on Piazza. Like they just kind of put this imaginary machine H in there,
Yeah.
and then they put an inverter in front of it, and then they say this doesn't work.
Mhm.
I don't understand how that works.
The reason that our construction works is that it fails on some inputs. It may work on some other inputs, but it fails on some of them. And so it contradicts the assumption that that machine that we just made is decidable because, is a decider because being a decider says that every input must halt correctly, say accept or reject correctly, but some inputs can't work.
But it seems like they're just putting parts together to make it fail.
Yeah, so the way that we we show undecidability is via reductions, which is trying to make the machine that we're building within the machine work in a certain way depending on whether, say, M accepts W, or the original Turing machine has empty language, or whatever. We're actually going to prove a general method, which is a lot easier to prove undecidability than doing these reductions. So reductions always work, but there's another method that works a lot of the time and is far, far easier to apply. Okay, any other questions? All right, so I'm going to do two more examples of undecidable problems. So the ones we talked about were ATM as well as ETM, emptiness for Turing machines. And we proved both of these were undecidable. So one thing that may very well be desired in, say, university programming classes is to figure out, does the sample solution code produce the same output as what the students actually submitted? That might be really nice in general to figure out, do they actually do the exact same thing? Or is it just that these particular tests are the exact same between the two programs? Are they really fundamentally the same program? And unfortunately, do you think that's decidable?
No.
No, unfortunately it's not. This is actually a very tough problem in general, but we call it Eq TM. So it's encodings of two machines with the same language. And I claim that this is undecidable. It actually turns out to be neither recognizable nor is its complement recognizable either, but we're just going to stick with undecidable for now. Okay, so we either could go via the method of proving via how we proved ATM was undecidable to prove this is undecidable, but I don't think that that's very desired. So what is the other way we can prove a language undecidable that we've done twice in the last class? Or once, I guess. Yeah, so we assume that there is a decider for the language we want to prove is undecidable. Then we can now make a decider for a known undecidable problem. So the ones we know right now are ATM and ETM. Well, this is going to start becoming more of a problem as we go along because now we got to figure out which one of these is the easiest to reduce from, right? And we actually could use both. Well, we could use any one in general, but it's just figuring out which one is the easiest here. So we could do ATM, but we're going to stick with ETM right here. So the idea here is I assume I have a decider for Eq TM, and now using that decider, I'm going to make one for ETM. But that obviously can't happen because ETM is undecidable. So, proof. Suppose that D decides Eq TM. I think I've said this before. The hardest thing about this class is coming up with names for things. Yeah, so you run out of names very quickly when you do these types of proofs. All right, so I assume that D is a decider for Eq TM. And then now what do I got to do? Well, show it's not possible by doing what? Yeah, I need to make a machine that now supposedly can decide ETM. The thing I already know is undecidable. But obviously there's no decider for ETM, so that'll contradict my assumption. So to decide ETM, what does a supposed decider for ETM take as input? Yeah, just a single machine here, right? So on input M, and I don't really need to say this, but where M is a TM. So I need to be able to use this supposed decider for Eq TM some way to figure out whether M has empty language or not. That's my goal. Well, what if I fed M into the decider D? Would that tell me anything about whether M has empty language or not? No, that wouldn't tell me anything. Well, so yeah. All right. So I need to come up with another machine so that'll actually help me figure out whether M has empty language or not. So eventually I'm going to say run D on, and I'm going to provide it with two machines. Well, I think it is pretty obvious that I need to have M be one of those machines because it's going to help me decide something about whether it has empty language or not. So I'm going to have M be one of them. So let's see. If M has empty language, what do you think D should say on whatever two inputs I give it? Well, it should say either accept or reject. Well, if we want it to say accept, that means that M has the same language as the other one. Conversely, if M does not have empty language, what should the other one have? Non-empty language. Okay? So what we want here is to have the second machine accept nothing. So let T be a TM that rejects everything. And now I'm going to have that be my second machine. So let's figure out why we're trying to do it this way. So I'm going to try to use my decider for Eq TM to figure out something about whether M has empty language or not. So the way we did it here is, of course there are other ways you can do it, but the way we did it is, if it does have empty language, then I want D to say yes. If it has non-empty language, I want D to say no, they don't have the same language. And the only way that the second machine could work so that those answers are correct is if it has empty language. So let's see. Can D run forever? No, because it's a supposed decider. So if D accepts, in the other case, if D rejects. Well, if D accepts, what do I know about M and T? Well, let's see. What do I know about M and T if D accepts? They have the same language. Okay, well, what does that tell me about M? Well, I don't know if it explicitly rejects everything, but what is its language? It's the same as T, which is empty. So what should I say for my decider for ETM? I just determined that M's language is empty. So I should say accept. Of course, there are other ways you can do this, but this is one of the more intuitive ways that I know. All right, if D rejects, then what do I know about M and T's languages? They must be different. Okay, well, if M's language is different than empty, can it be empty? Please say yes. No. It's been a long week. All right. Well, if M and T have different languages, then can M's language be empty?
No.
No. So what should I say for my decider for ETM? Reject. Okay? Well, I just made a decider for ETM. Can that happen? No, so what can I claim now? Yeah, D cannot exist. So D cannot exist because if it did, then I can make this decider for ETM.
And we have to cite that we know it explicitly that ETM is.
Yeah, because we proved it, yeah. So I should say cannot exist because ETM is undecidable. And so therefore I can conclude Eq TM is undecidable.
So can you walk back through why you started at EQ and you went to E? Then? 'Cause we're
Yeah.
looking for equivalence, which means they should have the same language.
Yeah.
Which means that they should both.
Yeah, I could have easily done ATM here. It would work perfectly fine. But you would have to work on it a little bit more, but ETM will make things a lot easier here. The way we chose ETM was, well, the inputs Turing machine's language is either empty or not. So the two possibilities are the two possibilities we want the supposed decider for Eq TM to be. And the only way that that could happen is for the second machine to have empty language. Like for instance, if I did all TM, where I test if the input Turing machine's language has every string in it, then in this case, I would have T be a Turing machine that accepts everything. It's just those two possibilities I'm mapping, so it's called mapping reducibility for that reason. I'm mapping those two outcomes to what the supposed decider is going to say. So like if it really is empty, I'm going to have D say it accept. If it's non-empty, then I want D to say reject too. Okay. Other questions?
And this is the type one for, you said you're going to show us another way of doing it.
No, I'm going to show you two languages. Well, and then I'm going to show you in the, or I can just go to that way. I might be able to not cover it. Well, let's start anyway. Well, let's see. Well, we talked about emptiness of Turing machines, testing whether a given Turing machine has empty language. That's undecidable. What about, say, testing whether an input Turing machine accepts the empty string? Do you think that's decidable or no? It actually turns out to be no as well. Testing whether an input Turing machine accepts everything. I just outlined to show how that's not decidable either. Testing whether it accepts at least 100 strings. Do you think that's decidable?
Yes, it's finite.
No, at least 100.
At least.
Even if it's exactly 7 strings, that's not decidable.
So that's why the 3-string thing would be the problem.
Yeah.
So Turing machines are just in general not decidable?
It depends on the question that's asked. So we're going to be talking about the languages of Turing machines, and asking any question that's worth your salt about it, that's undecidable. So that's one of the famous theorems we're going to talk about next. All right, so it seems like anything that we ask about the languages of Turing machines seems to be undecidable. What if I asked you, does this Turing machine have at least 7 states? Is that decidable?
Seem to be leading us that way on the data exercise.
Yeah, it is decidable. Why? Just look at the input that's given. Count the number of states that are listed there. But asking anything, it seems, about languages of Turing machines seems to be undecidable. So now this will seem like a stupid question, but suppose I asked you, does this Turing machine that I give you have a language? Any language at all? The answer is always yes. So is that decidable? Yeah. So we gotta be able to be a little bit careful. We can't just talk only about languages. We gotta be a little bit more restrictive in how we phrase things. So I want to talk about something called properties of Turing machine languages. So the way we want to phrase this is the only thing that should matter, whether or not a certain Turing machine is in some language that we care about or it's not in that language, is only dependent on its language. It's nothing to do with its description or anything else, only on its language. So a property of TM languages, let's call it P, is a set of TM descriptions. So it's just a bunch of Turing machines as their descriptions, so that for any two TMs M1 and M2 with identical languages, so what I'm trying to set up here is that the only thing that should matter is your language. Okay? If I have any two Turing machines with the exact same language, then they're either both in the language or both not. So it can't be the case that one of them is in the language and one of them is not in the language, because that would depend on something else other than the language. So what we're going to say is then either both descriptions are in this property of Turing machine languages P, or should put a 2 there, or they're both not in P. It can, if it's an actual property of Turing machine languages, then it can't be the case that one of them is in P and the other one is not. Because then, of course, that would depend on something other than the language. Okay? Super. Any questions about that? All right. So now we need to be able to restrict the types of properties that we are going to be talking about. Because as I mentioned, if I talk about all Turing machines that have any language at all, that's decidable. So we need to be able to talk about what are called non-trivial properties. Okay? So a non-trivial property has at least one Turing machine that is not in P and another that is in P. So, of course, what are called trivial properties are those that have either every Turing machine in the language or none of them at all. Because then I can just say for the first one, accept on whatever input, and the other one, reject on every input. And those are clearly decidable. But for those that are non-trivial, at least one Turing machine doesn't have the property or is not in the language, and another one that is in the language or has the property. Okay? So, like for instance, ETM is a set of Turing machine descriptions. Of course, there are some Turing machines that have empty language and thus are in ETM, and some that are not in ETM because they have non-empty language. So ETM would be a non-trivial property in this case. Would ATM be a non-trivial property? Be careful. Is it a set of Turing machine descriptions? what are you given for ATM? A machine and an input. Is that a set of Turing machine descriptions? No. It's a set of descriptions that have a machine and an input, so I can't qualify it under a non-trivial property. What about Eq TM, where I have two Turing machines? Is that a set of Turing machine descriptions? Well, it seems like it, but it's not single Turing machine descriptions. So things of the form, a single Turing machine description such that whatever the condition is, so that's good. But if we want multiple Turing machines in the description, then that's not going to work, because we need to talk about the language of the machine. Well, if I'm given two Turing machines, which one do I pick? Right. So I can only talk about single Turing machine descriptions. Okay?
Even if you know what the language is, for the two and that like those two have the same language,
Yeah, but what's the language of M1, M2?
like together.
Yeah, what's the language of two arbitrary Turing machines? I don't know. I know a single one, but I don't know multiple ones. And yeah, and the way we described it here and here is single machines. All right, any questions about that? All right, so this is one of the most important theorems in this area called Rice's theorem. It's actually a solved exercise in CSE chapter 5. So if you want to take a look, go ahead, but we'll prove it here as well. It says that every non-trivial property of Turing machine languages is undecidable. Not just some of them are undecidable. Every one is undecidable. So if you want to ask, does this Turing machine accept at least 100 strings? Undecidable. Does it have an infinite language? Undecidable. Does it have in fact a regular language or a context-free language? Undecidable. Every single one is undecidable. That's non-trivial. Okay? So instead of just proving a few and then saying, okay, yeah, this is the general flavor of how things are going to go, we'll actually prove that every single one is undecidable. So I'm not going to prove it here today because you have other things on your minds, clearly. But let's actually apply Rice's theorem without actually having proven it, and I'll prove it on Friday. How's that sound? All right. So that example that I gave, that testing whether a Turing machine has regular language or not, that would be analogous to saying, I have this complex computer program, could I transform it into a DFA, which is a lot simpler structure that I can analyze? And that's undecidable. So what I'm going to call regular TM, so it's a set of descriptions of Turing machines, M as a TM, and its language is regular. Okay?
So is the goal we break those up and then independently prove that each of those on the right-hand side is non-trivial, and then you're done?
The whole language is non-trivial.
Oh.
You prove it's a property of the language of Turing machines, and then you show it's non-trivial, and you're done. You don't have to make another Turing machine. You just prove those two things, then say, by Rice's theorem, this is undecidable. So it's a lot easier. Well, can I even begin to apply Rice's theorem?
Yes.
Yeah, so is it a language of single Turing machine descriptions? Yeah, certainly. So I can at least try to apply it. So it's a nice initial check. So the first thing I need to show is that this is a property So ignore non-trivial for a second. This is a property of TM descriptions. Oh, sorry, TM languages. Well, what does it mean for some language to be a property of Turing machine languages? Well, it says, if you have any two machines with the exact same language, either both are in the language or have the property, or neither are. Okay? Could it, so let's see. If L of M1 equals L of M2 for arbitrary two Turing machines, could it be the case that M1's language is regular and M2's language is not regular? No, because they're the same language. So either both are regular or neither are.
And we can say that because we're using the LM, the regular TM's LM definition on M1 and M2.
Yeah, so for two arbitrary Turing machines, if they have the same language, then they're both either regular or both not regular, by definition. Yep. Okay? Have I shown everything I need to show? What thing did I forget? Non-trivial. I haven't shown that it's a non-trivial property yet. So what do I need to show so that it's a non-trivial property? What's that? Well, I need to show you two machines. I need to show you one that has regular language and one other one that has non-regular language. Is there an example of a machine that has regular language? No, sorry, a Turing machine, example of a Turing machine that has empty language. Oh, sorry, has regular language. How about just the machine that rejects everything? That's a perfectly valid example. So let M1 be a TM that rejects everything. Then, because it rejects everything, it has empty language. And so, does it belong to regular TM? Yeah, because it has regular language. Good. So, I can now say that M1 belongs to regular TM. Okay, now I need a Turing machine that doesn't belong to regular TM to show it's a non-trivial property. Is there an example of that? Any example? 0 to the n, 1 to the n. Perfect. So let M2 be a TM that accepts the, I should say recognizes, but the language 0 to the n, 1 to the n, then it's pretty obvious that M2 should not belong to regular TM because it doesn't have a regular language. So M2 does not belong to regular TM. So I should note that 2 is for non-trivial. That's what I wanted to show in part 2. Okay, well, did I show that it's a non-trivial property of Turing machine languages? Yeah, I showed it in the first part was it's a property of Turing machine languages, and the second part was showing that it's non-trivial. So by Rice's theorem, what can I conclude? It's not decidable. So by Rice's theorem, the most 3 important words of this whole thing, regular TM is undecidable.
It seems like you just created two things and just said, oh, it's undecidable.
Yeah.
I don't understand how that's actually proving.
It's applying the theorem that says every non-trivial property of Turing machine languages is undecidable. That's what the theorem says.
Yeah, so on number one, I'm following. So we're saying that we started with regular, right?
Mm-hmm.
So you picked an M1, right?
Yeah.
You said
So
that-
the first part, first and second part are completely disjoint.
yeah.
Think of them
So
differently.
the first one makes sense to me, but on the second one, you're just picking two things.
Yeah,
Like,
I
you're purposely picking one thing
Yep.
that doesn't have a regular language.
Yep. I need some machine that's not in the language, and I need one that is. Okay.
And how does that prove the regular?
So in the proof of Rice's theorem, we're going to be using a reduction from ATM. And what is going to go on in the behind the scenes is that we're going to have the machine that we build inside behave like one of the machines that's in the property. Then if M accepts W, it behaves like the other one. And so it's just a reduction behind the scenes. The reason we pick one that's in regular TM and one that isn't is that we can actually differentiate between those two cases behind the scenes. But this is a lot easier than making an actual machine that's using a supposed decider.
So basically, all this is saying is as long as you can find any machine, doesn't matter what it is.
Yep. That's its description is in the language, in this case regular TM, and another one that isn't.
Okay, so then how is M2 in a language?
M2 is not. M2 I said is not in regular TM
Yeah.
because it doesn't have regular language.
I don't understand how it's proving that.
I'm just applying the theorem which says every non-trivial property is undecidable. And just because now I showed it's a non-trivial property, it must be undecidable by the theorem.
Or regular TM is the non-trivial property.
Yeah.
Right?
We prove that it is a non-trivial property. Yeah.
So you're taking regular, right? And you're saying here's one language that is in it, and then here's one language that is not in it.
No, one machine that's in it, yes.
Okay, sorry. One machine. Here's one machine in it, and one machine not in it, and
Yeah.
therefore it's undecidable.
And it's a property of Turing machine languages, yes.
That the languages are the same.
Yeah, for any two arbitrary machines, yes.
Okay.
Yeah.
So when you're dealing with encoding that more than one machine, you use reusability.
I didn't hear you, sorry.
But if you're dealing with an encoding that's more than one Turing machine, then your only approach is reusability.
Yeah, that's the only one. Yeah, correct. Other questions? All right, so I'll prove that next class, and I think we should take a break now.